Hello everyone, welcome back to another video. Today we are going to be using the Crank-Nicolson method to do some implicit differencing for the same situation that we've been looking at for the past couple of videos. Once again, we are going to be having a bar at room temperature and we are going to begin heating both sides, and we are going to be looking at how that heat is going to diffuse throughout the bar, and then we are going to model it looking at Python. So in the last few videos, we use an explicit differencing method to kind of simplify our equation. And while that did work pretty well, we ran into some troubles with our stability whenever the time step, or our R value, became greater than 0.5, all right? So today we are going to be using this Crank-Nicolson implicit method in order to try and create a model that doesn't quite have the same issues with stability, all right? So we are still going to be trying to simplify over here our secondary differential equation with this temperature relating to the position over here. But with this method, we are going to be taking an average of the temperature at the same position, but at different times, right? Here we have the temperature at this position J at the first time period, and then we are taking that temperature at that exact same position at that next time step. Because once again, we are still going to be splitting up our time and positions into evenly spaced steps. So that's what we're going to do. And then we're going to be dividing it by the change in time, which is going to be the difference between n plus 1 and n. All right? So we will go ahead and answer what this equation is going to be, and we'll cut to that once we got that written out. All right, so we've gone ahead and written out our answer over here for this average of the temperature at the same position at different times. And it's important to note that this is not one big division fraction over here. This is supposed to be over here, but we kind of ran out of room, so I just kind of wrote it under. So do note that this is not a big fraction right here. This is this term being added to this term, and then over here you have your thermal diffusivity over 2 being multiplied by all of that, all right? So our next step is we are going to want to kind of get common terms out of this and try and simplify our expression over here. So we can, the first thing we can do is we can bring out our change in position squared, bring that out since that is a common denominator that these both have. So we can bring this fraction out and bring it out to our expression out front. So that would turn this into the thermal diffusivity over 2 times the change in position squared. And then over here, we can multiply the change in time over to the other side. So we'll go ahead and do that. We'll erase this over here. And we'll go ahead and erase this over here since we're not going to need those anymore. So this expression out front would then become the thermal diffusivity over the change in temperature all over 2 times the change in position squared, like so. And if you remember our last few videos, we said that our R expression was equal to this minus the 2 over here. So we can say that this is going to be equal to R over 2. And when we go into Python, we are actually just going to use mu to represent R over 2. We're not going to be coding it as R over 2. This is just going to be used as mu or u, since we can't really use the Greek alphabet in Python. So this is just going to be represented by u right here, all right? So then we're just going to have u out in front of this, like so. Actually, we'll just write up as u. Don't want to get mu in here. Don't want to complicate things too much. Go ahead and make this look a little cleaner so we can visualize what we're working with a little easier. Shorten these up. So this is going to be our expression right here. And the next thing we are going to want to do is we are going to want to get all of the n plus 1 terms over here onto the left side and all of our regular n terms onto the right side, all right? So we're going to want everything at the initial time to be on the right side and everything at our later time step to be on the left side. so that we can set up our matrix that is going to be solving for us. So we're going to go ahead and do that now, and we'll cut to when we have all that written up. Once again, we are just going to be doing some simple addition and subtraction in order to get all of our n plus 1 terms over to here, and then getting all of our regular n terms over to the right side. So we'll do that now. Alright, so we'll go ahead and start moving all of our n plus 1s over here to the left side. And to start, we'll go ahead and put our j plus 1 terms on the left, then our regular j terms in the middle, and then our j minus 1 terms on the right. So it's kind of aligned with how you would look at it on the bar. Our biggest position values will be on the left, and then we'll work our way down. So it's kind of linear like it would be on the bar, so we'll do that now. We'll start by subtracting this t, j plus 1, n plus 1 over. And we also have to multiply everything by u, so we can't forget about that. So this would be negative u, t, j plus 1, n plus 1. Alright, we've got that knocked out of the way. Alright, and then we are going to be adding a 2. It looks like we forgot our t over here. This should be negative 2t. Looks like we also did the same thing over here. This should be a t in there. Alright, so we are going to be adding our 2, j n plus 1, and then we also had this over here. So this is going to become a 1 plus 2u because this is being added over, and we also have to multiply by u. So we can go ahead and just put that 1 plus 2u out front. And then this is t, j, n plus 1. Alright, that's that taken care of. And that taken care of. Alright, and then over here we have our j minus 1. So all we have to do there is multiply it by u and then subtract it over. So we'll go ahead and do that. So this is going to be minus u, t, j minus 1, n plus 1. That's that taken care of. Alright, and then over here we only have this 1, j plus 1, so this is just going to be remaining here. All we have to do is multiply that by u. No real changes there. So we'll just go ahead and add that. And then over here we do have this negative 2t j of n, but we also have this j of n over here. So we're going to have to add this over. So this is going to become a 1 minus 2u since this is negative, but this is going to become positive since we're adding it over. So this will be 1 minus 2u t j of n. So that's all this taken care of. And then finally, we just have our j minus 1n. That is all by itself, so that'll just be added and multiplied by u. So plus u, t, j minus 1n. And there you have it. This is going to be the equation that we're going to be working with our matrices. I'll go ahead and cut it here and kind of make this a little cleaner to look at so it's not going off into the second line. And then we'll go ahead and start working on our matrices and get that all sorted out. Alright, so before we go ahead and start setting up our matrix that we're going to solve, we're first going to think about our bar and think about the positions that we are actually going to be wanting to solve for the temperature, alright? So we said that earlier in the last few videos, we have this bar and we are going to be having a certain temperature that the right side and the left side are going to be set to, a TL and a TR. And these are going to be constants, this TL and TR right here, and they're not going to be changing, so we don't need to solve for those, alright? We are going to be solving for our position steps all the way out between TL and TR. These are what we are actually going to be solving for, right? So we are going to need to solve all the way from this first position all the way out to this other rightmost position, all right? And if you remember in the last video, we had 20 steps, but once again, we didn't need to solve for the leftmost step and the rightmost step. We needed to solve for those 18 steps in between. So if we're using the same setup that we used for the last two videos, we're going to be needing 18 equations in order to solve for that, going all the way from t1 to tn minus 1, because over here, this is going to be your nth step, and this is going to be your 0th step. So we're going to need to solve all the way from 1 to n minus 1. So we'll go ahead and hop into the matrix now and start trying to solve for it. We'll go ahead and set up our unknown temperature column right here. And this is just going to be going from T1 to Tm minus 1, because once again, we don't need to solve for T of 0 or T of n. Those are already known. So this is going to be going all the way from T1, T2, T3, all the way down to T of n minus 1, because those are all the temperatures that we need to solve for. All right? Now, to get our left box over here, we are going to be plugging in our T2s, our T3s, and so on into our left side equation over here for our temperatures. And then we're pretty much just going to be putting in whatever is left outside of the temperature into that column, right? So we'll just go ahead and look at T2 to start out with. So here we have T2, and we plug that 2 in for J, right? So you get 2 minus 1 when you plug this in for here, and that gives you 1. And outside you have this negative U out front. So in the first column, you would put negative U for T2. And then over here, you plug this 2 in for J, and this is just a normal J. It's not being added or subtracting anything, so that's going to be a 2. So this would go in the second column. And then you have a 1 plus 2U out here. So that is what we put for the second column. We'll go ahead and scooch this over because we are going to need more than 3 columns in order to visualize what is going on, the pattern that's going to be forming with this matrix. So then we go over, we have 2, we plug that in for J. This has a plus 1, so that 2 becomes a 3. So this will go in the third column, and once again we have a negative U. Alright, let's move on to T3. T3, you have this minus 1 right here, so that's going to become a 2. So this will go in the second column, and we have a negative U. And then you move over, T3. This is just going to be a 3 since it's not being added or subtracted by anything, so that becomes a 3. And then we have 1 plus 2U. Then you take 3, you add 1 to it, that becomes 4. We have a negative U there. And that's what you get. Alright, so what's going to happen when we go T1? Well, you have 1 and you plug this in for J minus 1. That's going to be 0. You're not going to be able to do that, so we're going to skip that one for now. You have 1, you plug it in for J right here. That is just going to be 1, so this is going to be what goes in the first column, this 1 plus 2U right here. Alright, and then you have 1, you plug it into J plus 1, that gives you 2, so negative U will go in the second column, like so. Alright, so this is going to be the pattern that's going to be forming, alright? It's going to kind of be shifting diagonally down the matrix. So that is going to be the pattern that is forming right here. So let's say you wanted to plug in n minus 1. You wouldn't be able to plug that into j plus 1, right? Because that would give you n, and you don't really want n. So you wouldn't be able to do that. You'd just be able to plug it in for j and j minus 1. And then we'll go ahead and start solving our right box over here. Now, this right box, we're not doing matrix multiplication with this over here, so the order in which we put the terms isn't really going to matter. So we're just going to kind of be plugging this into the right side of our equation and just writing down what it gives us, right? So we'll go ahead and start off with T1 over here. So what's going to happen when we plug in T1 is this is going to become 1 plus 1. So this is going to be UT2. Pretty simple. All we're doing is adding 1 to our temperature over here because the position is getting shifted over 1. Then we plug it in for here. This is going to be 1 minus Tu times T1 because the position is remaining the same. All right, and then over here we subtract 1. That gives us T0, so this is going to be UT0. This is just going to be the temperature of the initial position, or the leftmost position where we have the constant temperature, UT0. All right, then we'll do the same thing for T2 down here. This is going to be the same thing, except all of these temperatures are shifting over a position to the right. So this is going to be UT3 minus 1 minus 2U of T2 plus UT1. All right, and then this pattern is going to be continuing all the way down until our final position over here at n minus 1. It's going to be the same thing, except all of these temperatures are going to be increasing by 1 as you move down the matrix, all right? So what is going to happen when you get here to Tn minus 1 is when you add 1 to this over here, this is just going to become Tn, all right? So this will become UTn, and then it's going to go down from there, so it's going to become n minus 1, n minus 2 right here, because again, it goes down by 1 as you move further along. So this is going to be 1 minus 2u of n minus 1, and then plus u of Tn minus 2. And there you have it. This is going to be the pattern that our matrix is going to be forming over here. All right, so earlier on when we were doing this left side, we plugged in T1 to this J minus 1 and got T of 0. And we didn't really want to do that because that was a constant and that wasn't going to be changing. So that was going to screw with our matrix multiplication. But what we can do there is when we plug in T1 and get this negative UT0, we can add that to both sides in order to get that over here. So that we would have a negative UT0, but since that's a negative, we would have to add it to this other side, and we would get another UT0, which we already have over here. So this would actually become positive 2UT0. So we'll just go ahead and write this 2n over here. And likewise with this bottom equation over here, when we had this n plus 1, we plugged it in for j plus 1, and that gave us n, which we didn't want because Tn is that rightmost position where the temperature is also constant, which would also screw with our matrix. So we would also add over this ut of n, which we already have over here. And once again, we would add it over because this is a negative utn, so we add it to both sides to cancel out over here, and that would give us another one over here, which we would add to our already existing UTN to create 2 UTN. And there you go. That is going to do it for our matrix. This is all written out. These are the patterns that are going to be forming. Now we'll go ahead and code this up into Python so that we can create our implicit model for how this heat is going to diffuse throughout the bar. And we'll go ahead and hop into that now. Alright, so we are over here in Python, and I've gone ahead and copy and pasted all of the coding that we did from our video 2 videos ago, because it's going to be pretty much the same method that we used. I have gone ahead and imported solve banded from scipy.linalg. This is what we are going to be using to solve the Crank-Nicolson matrices that we created earlier on the whiteboard. And we'll go ahead and take a look a little bit more in detail at the solve banded function over here. So pretty much what this is this is going to solve our diagonal matrix that we had. We did have 3 diagonals. We had negative u at the top and bottom diagonals, and then right in the middle we had the 1 plus 2u. So if we look, the middle column is going to be, the middle diagonal is going to be running through all the columns. The upper diagonal is not going to be showing up in our first column, and then the bottom diagonal, which was also negative u, is not going to be showing up in our last column, but will be there in our first column, all right? So we've already gone ahead and imported the function that we're going to need. The only thing that we're going to have to change up here is we are going to have to replace r with u, because we did come up with a new function, and it's pretty much the exact same thing except all over 2. So we'll get this all divided by 2, and there we go. Alright, so our first step here is we are going to need to create a matrix full of zeros. So we will go ahead and do that now, and we will call that this new matrix A. So we'll give ourselves some room up here. Alright, so A is going to be equal to np.zeros. This is just going to create a matrix that is filled with zeros. And over here, we are going to need to define how many rows and columns we are going to need. So we are going to need 3 columns because, again, there's 3 diagonals. And for the number of rows, we are going to need the number of steps that we have minus 2, because we're not going to need to do the final one or the beginning step because we already have those. Those are at a given temperature, TR and TL, so those aren't going to be changing, so we're not going to need to worry about that. So over here, we had a 20-meter bar, and each position step was 1 meter, so 20 over 1, that's 20 different steps, which is going to be 18 steps for this situation. But we will just call this n minus 2 in case we wanted to mess around with how long the bar is going to be or what the length of each position step is going to be. So we will just leave this as this for now. The next thing we are going to need to do is we are going to need to create our left matrix, which is going to have all of our negative u's and 1 plus 2 u's, our diagonals in it. So we'll go ahead and create 3 of these. We need brackets there, not braces. All right, we'll have one for columns 0, 1, and 2 because Python notation, the first row and first column starts at 0 instead of 1. So we'll create 1, and then finally 2. All right. And then we are going to say that this is going to be equal to negative u and negative u. And then the main middle column is equal to 1 plus 2 times u. Get some parentheses going around this. 1 plus 2 times u, like so. All right. Now we are going to need to define what columns these are going to be showing up in. All right, so our first one, our negative u, if we go back over here, we can see that this is not going to be showing up in our first row, but is going to be showing up, our first column, excuse me, but it is going to be showing up for all others. So in order to define that, we are going to say that this is going to show up in 1, and then and then we're going to use a column to say that it shows up at every column, starting at the second one and going all the way out to the ending, like so. All right, and then for our other lower column, we can see that it is going to be showing up in the first one, but then it is not going to be showing up in our last one. So in order to say that, you are going to put -1 colon like that. All right, so we did make a little mistake. We did put the colon on the wrong side. This would input it into all of the columns starting at the second to last column and then all the way out, which is not what we want. We want this to end at the second to last column and input for all of the columns to the left of that. So we're going to need to move all the colon to the other side. And then for our middle diagonal, we are just simply going to put a colon because this is going to show up in every single column. So we're going to want that to input for everything. All right, this is all looking good. This is our left-sided matrix that we came up with earlier on the whiteboard. Now we are going to need to solve it, and we are going to create a new matrix called B for this. So B is just going to be equal to that to pretty much what we came up with earlier in the whiteboard. So we'll go ahead and input that now. All right, so for our B, if you remember earlier to our whiteboard, the left column within our right matrix, that was simply U times T. So we'll go ahead and input T. And then that T actually had a range from 0 to -2. Actually, no, I believe it was from T to the end, right? Or 2 to the end, excuse me. So yeah, this started at the second value, T2, at the second position, and then went all the way to the end. So we are going to need to do it for all of these values. And then we also had a second U that went all the way from 0 to the second to last value. So we'll go ahead and copy and paste this over. And then we will get some space so we can visualize this a little bit more clearly. So this is going to go all the way from the initial T value all the way to the second to last value. So this would be represented by :-2. All right, and then in the middle, we had our 1 multiplied by 2 times U, or being added to 2 times U, excuse me. So we'll have that. So this was 1 minus 2 times U. This should be a 2 times U. All right, that is looking good. And then this was multiplied by T from the first value over to the second to last value over. So this is going to go from 1 to a -1, like so. All right, and this is our B all wrapped up. But if you remember, we did have to, multiply some of these values by 2 earlier on the whiteboard, because we were using values on our left matrix at the endpoints, which we didn't want to do because those were constants, so that would have screwed with our matrix math. So we added them to both sides to cancel out on the left side, and that created 2 times U times T over here on the right side for the first column, and 2 times U times T on the left side over here in the bottom column. So we are going to have to account for that. All right, before we go ahead and hop into accounting for what we just talked about, we did make a little error over here. We are going to need to include a 0 so that it knows to start from the first column. So we'll go ahead and add that. Now we'll move on to accounting for multiplying this by 2. So we are going to need to do one for 0, which is the first position in the top row, and then we will do one for B, -1. Get some brackets around that. All right, and this is simply going to be equal to itself, and then we will also add this to U times T of 0. And then we'll do the same thing down here except for -1. Break that in there. All right. -1 and then -1. All right. So we've got all of this wrapped up right here. Now we can go ahead and delete our function that we did to create our graph in the video 2 videos ago. Not going to need that anymore. All right, here we go. All right, and now we're actually ready to bring in our solve banded function over here. So we'll go ahead and get to that part now. All right, so now we are going to go ahead and use our solve banded function over here, and we're not going to put it into this graphing function over here right away. We're just going to copy and paste our code down here just to check and make sure it's running correctly. But first, before we do that, I did already run through this and realize that we need some extra parentheses up here. in order for our initial matrix to be created properly. So we'll go ahead and do that. We'll just run through all this, make sure it's all running good. All right, and it is. All right, so now we are going to go ahead and use our solve banded function. All right, and then for our initial parameter that we have to put in the number of non-zero lower and upper diagonals. This is going to be easy for us. We just have one of each. So we just say parentheses 1, 1. And then we have to input the name of our banded matrix and then our right-handed matrix, which was just A and B for us. And that's going to do it for our banded function over here. And before we test this out, let's go ahead and change up some of our parameters over here, because the whole reason that we are doing this video is because we want to create a function that will work properly when you have a larger time step than half a second. So we will change this from half a second to 1 second, and then we'll just go ahead and change the initial temperature from 20 to 25. And then down here we'll change the range function from 50 and the divisor from 10 to 50. All right, and then we'll need to, of course, run through this so it knows to use these new parameters. Update this, and we'll see how this is running. All right, looking like it's running beautifully here. As you can see, the heat is diffusing a lot faster at the endpoints nearer to where the bar is being heated and not so much in the middle to start out with. All right, and yeah, all we are going to need to do now is we are going to need to input this function into our graphing for loop over here. So we'll go ahead and copy and paste this down here. All right, and we are going to say t from -1 to 1 is going to be equal to our solve banded function over here, because we only want this to, actually I believe this should be from 1 to -1, the other way around, because we are going to want to exclude the endpoints. We are only going to be changing all of our middle steps. The endpoints are going to be remaining constant at 50 degrees Celsius and 80 degrees Celsius. All right, so this should be it. We'll see what our graph is looking like here. All right, and there you have it. Nice, beautiful heat diffusion graph over here. Once again, as time moves forward, it is approaching a linear relationship between how much the heat is increasing as you move along the bar. And this is how you would perform the crank method to perform this function over here. This is what you're going to want to do in order to perform this with a time step greater than 0.5. In fact, you could do this method for pretty much any time step, but the larger the time step is, the more inaccurate this graph would become and the more inconsistencies you would get. But yeah, this is how you do it right here. In the next video, we'll be taking a look at what happens when you get towards the larger time steps, and I hope you guys will check out that video when it comes out. If you enjoyed the video, make sure to leave a like and comment down below what you guys want to see next. And take care and enjoy the rest of your day.